name is chu-carroll. I work for Foursquare, and I'm talking about an alternative build tool that we've been working on called Pants. And the goal of Pants is to improve what we call code hygiene. Okay? So to start off, this is probably somewhat unusual for this conference, but this is not really a talk about Scala. What this is a talk about solving the problems that we came across in using Scala in our system. So, what's happened to us is Scala gives us a lot of really great stuff. Parametric types with variants, implicits, type classes, all of that wonderful stuff. But as Dan noted in the keynote this morning, that stuff has a real implication in build time. And we need to control that cost in order to be able to successfully build a system. So the background. At Foursquare, our entire server is implemented in Scala. And I can't tell you exactly how big our code base is, but it's well over 100,000 lines of code. It's over 2,000 source files, and they're split up around 500 or so packages. When we started this, we used SBT for builds. And our clean build times, in other words, building fresh code, was averaging between 40 minutes and an hour. And this was on a massive machine. I mean, the highest end laptops that we could get. 16 gigabytes of memory, SSD disks, 4 cores with hyperthreading, and still we were talking about 40 to 60 minute build times. And to make it worse, almost any time that we changed any source file in the system, we'd have to recompile over 1,000 different source files just to get that incremental build. And so our incremental builds were over half an hour. And it's very hard for engineers to be productive when every time they want to compile their code, they have to sit and watch their computer thrash for 30 minutes. Why this happened, this is just a very small excerpt of the dependency graph from our system. I can't fit the whole graph on this screen. And this is so small, if you kind of look in the upper right corner, there's a little text box. That's the name of one of the components. So, what caused this epic disaster? It's not a particularly large code base. I mean, 100,000 lines, 150,000 lines, that's not small, but that's not huge. And if you did this in Java, you'd have a 5-minute compile. And you'd probably complain about it, taking 5 whole minutes. So, what the heck happened here? Part of it is just the fact that type analysis in Scala is very complex. And, when we instrumented things trying to figure out where the time was going, almost all of that build time is type analysis. But the second problem, which was a major factor, was that build graph, as you saw that crazy hairball, it was basically a giant clique. So that if you changed anything, you had to recompile absolutely everything in the system. And when type analysis time is exponential in the size of the type graph, having a dependency graph like that means that you have a pretty darn big thing that's gonna, that you have to analyze at an exponential time speed. So, the term for what's going on inside of there is poor build hygiene. So what do we mean by build hygiene? This is not a term I invented. This is kind of used a lot among people who build tools. But the basic idea is in your build tool, you have to declare what you use. So every buildable entity, which we call targets in our system, have to be declared and they have to be typed. Every target has to declare ahead of time exactly what it's going to depend on. And then using that information, the build system is going to verify correctness. It's going to check that every dependency is actually declared, and the compilations will fail if they're not. It will check that the dependency graph is acyclic, and it will verify that things depend on the right kinds of things. So you can't declare a dependency from Scala on C++ code. You could declare it on a J&I library, but you can't declare it directly on C++ code because that wouldn't mean anything. That would be an invalid thing. A quick explanation of why is this build hygiene stuff so important. I like to compare it to what we do in our programming languages. In our programming languages, we enforce code hygiene. We say that you have, especially in Scala types like us, you have to declare the types of things, and then the compiler is going to tell you if you do it wrong. You have to declare everything that you import, and the compiler is going to tell you if you didn't import something. So build hygiene is very much the same kind of thing, but applied to build time instead of applied to the actual code of the system. So declare your package dependencies, enforce rules, and make sure that they cause errors if you get them wrong, so that you know you got it wrong. So to explain the build tool that we're using, just a little bit of background, there are two fundamental approaches to how you can build things. They're called top-down and bottom-up. Top-down is basically what you're used to in most build systems. So you have a project which is some hierarchy of directories and files on a disk. It's got one thing off to the side that says how to build the project. So inside of there, you have the single centralized set of instructions for how to build. And inside of there, in some form, it says, essentially, here's a project that I want to build. Here's where you can find all the pieces. There's the source code. There's the tests. They're all over and here are the external things, the things not in my source code that I depend on. Now, please build it for me. This is what SBT, Maven, Builder, lots of things like that do. The bottom-up build is very different. In a bottom-up build, you don't really have a top-level build file. There is no single place that has the instructions for how to build your system. What you have instead is in each package, you have instructions for how to build that component. And then when you try and do a build, all of those instructions are assembled by the build tool. So the basic idea of the bottom-up build is the build description is distributed around the code. Each unit of code, each component, each package, whatever you choose to use, it has a build descriptor describing how to build that component. The build descriptors specify the other packages in the code that they depend on. And the build tool uses that to assemble a complete graph of everything in order to run the build. Because you have this componentized build instructions where each component declares its dependencies, it becomes very easy for the build tool to say, you're using something that you shouldn't, right? It's much easier for it to enforce your hygiene rules than it would be with a centralized. So in a bottom-up build, what happens when you want to actually build a system, the user has to specify a list of the compilation targets they're interested in. The system generates a transitive dependency graph for those targets. So it looks at the build file for the target you wanted, and anything that it declares as a dependency, it loads those build descriptions, and it combines that into a DAG, a graph of the build things that need to be built. It topologically sorts it to get a build order. Once the graph has been built and sorted, it checks it for validity to make sure that you're following the hygiene rules properly. And then it traverses the top sorted graph, one piece at a time, building the components. So the build tool that we use is called Pants. And this was originally implemented at Twitter. And we have an ex-Twitter engineer who knew about this, which is how we got into it. It is unfortunately implemented in Python, which is painful. But the fact is, it works. And it was easier to build on something that existed than to start from scratch. It's based on Blaze. We can't really take credit for any of the ideas in this. Because an ex-Google person went to Twitter and missed Blaze, started this, and then it came out. In the interest of disclosure, I was at Google at one point and I did work on Blaze, so I'm strongly biased in favor of this style of build. But basically, Pants is a very nice little tool. It gives a very clean declarative build language, and it makes it really easy to do this kind of hygiene stuff, which was just incredibly important for us. So this is basically what a build file looks like in Pants. This is a very simple example, but basically you put this in a file named build in a directory with the code. And this says, I want to build a Scala library. I want it to be referred to by the target name lib2. It depends on this other package. That's that explicit dependencies. And the source files are everything that's in this directory. The syntax is a little weird, like that globs line, because this is actual executable Python in the build file. For a slightly more interesting example, you can declare lists of source files, and then again, here's a Scala library. It declares dependencies, it declares the sources. Oh, the indenting is off there. There are two different Scala libraries here, I'm sorry. You can see right down here, can you see the pointer up there? This is the second one. This should have been backdented. And finally, one more example. This is from Pant's own build file for building itself. And it's just a short excerpt, but you can kind of get a sense of how it works. So you have different kinds of targets. Each target has its own set of components inside of Pants for building. So you know, in terms of using Pants, you know, there were a bunch of problems that we had to solve in order to make this work. And you know, the most interesting ones obviously are technical. One of the first things was that incremental Scala compilation, the main thing that does that is SBT. We were trying to get away from SBT because you know, SBT uses this monolithic build approach, and we want enforceable dependency checking. And the way that Pants wants to compile things and the way that Scala-C or Zinc actually wants to compile things can be different at times. So we really had to struggle with that. There were a bunch of things we had to do to get the performance of Pants to a point where we could use it. But the biggest thing is there are cycles in our dependency graph in the code. And these were perfectly acceptable in SBT. But when we want build hygiene, that doesn't work because a hygienic build graph, a hygienic dependency graph is acyclic. So we had to figure out how to rearrange our code in order to get rid of cyclic dependencies. And this is generally doable, but it can be a bit of work. But as I'll mention in a little while, it really does pay off. But so, you know, a quick example of what I mean by a necessary cycle. You know, we have some basic data types that we work with for our application. You know, in Foursquare, users check in to say where they've been, and then we save information about where they've been so that we can make recommendations to them for where they should go later. So a user has a method to retrieve a list of that user's check-ins. A check-in is an object that associates a user with a venue, a location where they were when they checked in. And a venue is able to say, you're able to ask a venue, who's checked in here? So, you know, this is a cycle. There's, you know, the way that we had to get around this was by separating data from behavior. And this is a very classic hygienic technique to break these dependencies. You have to split the behavior and the data into distinct traits. So what we did was we split user into multiple subtraits. There is a user trait which just defines the data fields of a user object. There's a behavior object which is the actual implementation or the actual declaration of the operations that we want to be able to do on user. And we have a concrete user impl object which actually has all the implementations of the behaviors and accesses the data fields. What this gives us is, you know, the user model. It doesn't depend on check-ins or venues at all. I'm sorry, that should be just user, not user model. The user implementation depends on the check-in model, but it doesn't, I'm sorry, on the check-in trait, the interface. Sorry, this is based on an older version of the code than the current. But it doesn't have to depend on the behavior of venue or the behavior of check-in. So the user itself doesn't have to depend on much of anything. The user behavior has to depend on just the data types for the venues and check-ins that it needs to be able to access. And the actual behavior implementation kind of depends on everything, but nothing depends on it. So we've broken the dependency cycle. So you can kind of just see the structure that I'm talking about here. We took user, and turned it into a pure interface that only declares data fields. We created a behavioral interface, which actually can reference other types. And then we have the actual implementations of it. Okay. The other really big thing that we had to deal with was a social factor. This is a very different approach to how you build systems than people are normally familiar with. Excuse me. And for example, right now, in SBT, when we were doing that, you typically say SBT compile, and that was it. It would build everything. You'd say SBT test. It would run your tests. With a bottom-up build, you don't have that. You have to say what targets you want to use. And that's a big change because now there's this piece of knowledge about the way that the build tool is going to work, which becomes essential knowledge for everyone working on the system. And that took some effort to get people to accept. The other really big thing was our code could not build in a hygienic build system because it had all of these cycles. So we had to do an absolutely massive refactoring effort just to clean that dependency graph in order to get it to the point where it could be built hygienically. So the point of all this was to try and speed everything up. We got an average build just immediately after starting to use pants. As soon as we got the code cleaned up enough that we could do a hygienic build in it, we managed to drop our build time by more than half. The dependency graph click now, this is up to date as of this past week. The dependency graph click used to be hundreds and hundreds of files. It's now down to 38, which is just a mind-boggling improvement. And we've got the typical incremental build. So if you change something and run a build, on average it takes about 6 minutes to do the build. And as I said, that was about 30 minutes before we did this. So this was a huge, huge result. And all of that performance gain really is coming from the fact that the size of the graph, the size of the type graph that the Scala compiler has to look at is drastically, drastically smaller. So what did we get out of doing this crazy thing? We got build times down, and they're still getting better. But a side benefit is, with SBT, the way that we were using it, essentially we had one build. You would say SBT compile, and that was it. But now we have a system where people can say, I want to compile just my component. And they can actually do that now very easily. It's a very natural thing to do. And we're kind of trying to turn our system into many smaller components. This just makes it easier to do that as we move along. The big question, was it worth doing? And to be honest, for build times, maybe not. I'm not sure. But the fact is, what really changed the build times was the refactoring. What Pants gave us was a way of checking that we were getting that refactoring right. In SBT, if we were trying to change it to reduce dependencies and we accidentally, didn't change the code in the right way to get rid of one, that would have been very hard to detect because it just isn't built to be able to check things like that. So, it made it easier to do what we had to do, but it wasn't really the thing that produced the results. But in terms of the maintainability of our code, I think this was absolutely a huge benefit. We have much more modularized code now, and we can enforce that kind of modularity, and that is a huge thing. It would be very hard, we have 50 or 60 server engineers. To enforce rules about how you can use dependencies among 50 or 60 people using a strictly informal approach it just isn't tractable. This tool makes it possible for us to do that. Come on. The obvious question that I was sure people were going to ask was, couldn't we just have done this with SBT? And the answer is, well, yeah, we could, but it would be harder. Just because SBT wasn't really designed to solve this problem. Obviously, from my bias, I prefer the pants approach to building. But I'm not saying that SBT is a stupid tool that no one should use. But if the thing that you really want to do is enforce build hygiene, it's much harder to do that in SBT because it wasn't designed to do it. Pants was, and that makes it much easier. In particular, the big reason that it's easier to do this in Pants is just that basic difference between a top-down build and a bottom-up build. Hygiene is a local property. It's a property of a specific package in the source tree. It's not a property of the entire system. So unless you have some way of talking about properties of small components, it's very hard to do this. And when you're talking about the property of a small component, it's best to do that local to the component. The bottom-up build makes that really easy to do because the build descriptor is with the code. The other big question, this was a question that many of our engineers asked us many times, couldn't we just do this automatically? And again, yeah, if you look at the set of imports in the source code, you can build up a dependency graph from that and then use that to generate the dependencies and have the same information that we're getting. And we do actually now have a tool that will generate at least a good approximation of a build file for a new component. But to me, this comes back to the comparison I made before about typing, right? Most of the things that we do with type declarations, you don't need type declarations to do that. I mean, people who write Clojure, people who write Python, they write code pretty well without it. But we like the hygiene. We like the rules that it enforces and the properties that it gives our code. So when it comes to build, I believe the same thing. Humans should be involved because these are real decisions about a system. And we want the decisions to be made intelligently by people. Stupid thing, sorry, family. So if you are interested in seeing Pants, this is where you can get it. It's on GitHub. The primary maintainer is Twitter, but the chief of engineering for Foursquare San Francisco is also one of the two tech leads of this on Commons. And last, of course, I'm obligated to mention this, we are hiring at Foursquare, and like I said, we do everything in Scala, and we're a really fun place to work. So, questions? Okay, so the question was, in a top-down build system, you could declare the system as a bunch of little jars. And did we look at that? The answer is yes, we did. It's much harder to enforce rules that way. So I mean, there's a couple of different ways that you can approach that. The build rules end up getting very, very complicated. If you want to do it so that you have one large source hierarchy and then you want to have separate builds for separate parts of it. It's hard to do that right. And it's also just harder to get additional rules into the system to say, if you see this kind of dependency, that's bad, get rid of it. So you definitely could do this, but it's a bit harder.
What about one approach is to split it into actual separate trees?
Yes.
You cannot have.
Right.
It's an informal thing.
Yeah. So yes, if you split it, the other approach is split it into many separate trees. But that's harder for engineers to deal with because when you're working on the system, suddenly instead of just knowing what package the thing you need to change is in, you need to know which compilation unit it's in. In this bottom-up approach, you don't need to do that. You can have one unified source tree. And that makes it a whole lot easier for the engineers. Yes, so Neil, one of the other Foursquare people here, just mentioned, if you're doing that approach with separate trees, if you decide that you want to split a single compilation unit into 2 compilation targets, you would need to split the trees, and that really would be painful. In this build system, you can even have multiple files in the same directory that belong to 2 different build targets within that directory. So the question was, I mentioned that we did some profiling of the compiler, and I gave some timing figures for things. So the data came from two different places. One of our engineers knows a lot of people at TypeSafe. He got an instrumented version of the compiler, which gave us profiled information. So, if you write to TypeSafe, I'm sure they'll share the same thing with you. But, it wasn't stock compiler. For the other data, it came from a bunch of different sources, but in particular, our build tool, we instrumented it so that we record the build time of every build that anyone does in a MongoDB table. So we have this data about how long things take, on average. Oh, the graph. The original version of that, the one that went up there, was just generated by parsing import statements, and then manually from that, well, not manually, but writing a program that from that generated a GraphViz data file and plotting it. So the dependency graph between targets has to be acyclic. But within a single target, everything can depend on everything. So what we did basically to switch to pants was create one huge target that we called the hairball. And everything was in it. And then we kept trying to prune things out of there. So right now, that hairball target is about 38 directories. Sorry, the question was, did we try to do a build in SBT after the refactoring, after the dependency reduction, to see if it would have been reduced? And again, the answer to that is no. But the Scala build component that we use, so Pants does its Scala compilation with a tool called Zinc. Zinc is essentially a front end to the SBT incremental Scala compile. So basically, we believe that the compile time under SBT would now be the same. The benefit that we get from Pants, as I said, isn't really the compile time, it's the enforceability of the rules that helped us reduce that compile time. So the question was, does Pants and Blaze have anything in common with the Go build system? The answer is no, nothing at all. When I was at Google, we talked to Rob Pike, who's the lead on the Go project. He hates Blaze. So, Blaze was optimized for a particular build system at Google, and he hates the entire infrastructure, so he didn't want to have anything to do with it. So, Pants incorporates Ivy. So, if there are dependencies that you need, external dependencies that you need to get for things that are outside, you can declare them in a Pants build file. There is a target type jar dependency, which takes the standard strings for the Maven Ivy package descriptors, and it will download them into your local Ivy cache and assemble the class path needed by both the compiler and to execute it. So setting up external dependencies is as easy as SBT, Maven, whatever. It's just standard Ivy. Any other questions? Okay, thank you very much.